Hey, we're back with Chemistry for Biologists, lesson number 3. Today I'm going to begin our discussion by comparing hydrogen bonds to covalent bonds. If you do not remember what a covalent bond is, please go back and look at the prior video, which is about making covalent bonds and how covalent bonds work. I'm going to begin by discussing just a simple analogy with African animals for you. I'll begin with a pair of elephants here, and I'd like to think of these elephants as making a set of covalent bonds because these bonds are strong bonds. The trunks are representing a pair of shared electrons, where one trunk would be one electron, the other trunk is another electron, and the elephants are sharing those electrons and making a really strong bond. Remember, these are the strong bonds. Molecules in general are joined by either covalent bonds or ionic bonds, so that's how you build those molecules, and in biology we focus very heavily on covalent bonds. In contrast to covalent bonds, we have hydrogen bonds. And hydrogen bonds are weak charge attractions. What you need to remember is that opposites attract. And so here the pair of giraffes, their necks are not intertwined, but they're knocking next to each other. And we could think of one giraffe as having a positive charge and the other giraffe having a negative charge. And the bond is being maintained by the charge attraction. A weak charge attraction. So why do we care about this topic? Why should we even care about hydrogen bonds? Well, hydrogen bonds explain why some molecules, different molecules and similar molecules, stick together. And in particular, the molecule that I want to focus on is water. Water is a super important molecule for biological systems. In fact, without water, we can't have life. That is the one pattern that we seem to see, that there is a direct correlation between water and life. And if you are interested in something like astrobiology, looking for life on other planets, one of the things that you want to know is, does that planet have water? In the case of our planet, we call it Earth, but really when you think about it, we are mostly water. I think the number is somewhere between 73 and 75% of the Earth's surface is water. I'm not 100% sure. You could ask our earth science teacher, I'm sure she would know. But the point is that we've got a lot of water, and life evolved in this aqueous water environment. In fact, our cells are mostly made of water. Our chemistry occurs in water, and water has some really unusual properties, and one of them is that it makes hydrogen bonds. So I want to look a little bit at water's structure, and I want to look at how those hydrogen bonds are formed. So just looking at the body of a bacteria, a typical bacterial cell is actually 70% water and 30% biological molecules, DNA, RNA, proteins, lipids, carbohydrates. But notice how much of that cell is water. So we got to look at the water to try to understand why water is the way it is. So this is a typical water molecule. Water has 2 hydrogens and 1 oxygen. Water is produced by a covalent bond, by 2 covalent bonds. That is, hydrogen shares 1 electron with an oxygen. Oxygen shares 1 electron with a hydrogen. So we could look at it like this. And the second covalent bond is the exact same thing. Hydrogen shares one electron with oxygen. Oxygen shares one electron with hydrogen. But here is the thing. The sharing is uneven. The end result of this uneven sharing is that the oxygen side has a weak negative charge, and each hydrogen side has a weak positive charge. And I want to look at why that charge difference exists. So let's look a little bit more carefully at a water molecule by looking at its elements. So at the very top here, you can see oxygen. So I'm going to put a big O in here for oxygen. Oxygen has a total of 8 electrons, 2 electrons on its inner shell, and 6 electrons on its outer shell. But that oxygen has 2 vacancies. Now, because of oxygen's unique properties, it has a really strong desire to fill those vacancies. And that desire to fill its vacancies is referred to as electronegativity. We say that oxygen is super electronegative. It's one of the most electronegative elements in the periodic table. It can be quite destructive to your tissues. If you've ever heard of free radicals, oxygen is something that is attracted to free radicals, and therefore electrons will go flying through your body and punch holes in cells in order to bond to oxygen. That's how aggressive oxygen is for its electrons. On the other extreme, hydrogen is a little bit loosey-goosey with its electrons. Now, it's not willing to give oxygen its electrons, but it's willing to let its electron wander closer to the oxygen. So you can imagine that this one electron will actually kind of drift and lie a little bit closer to the oxygen. The same thing is going to happen here with the second hydrogen. The electron is going to kind of drift closer to the oxygen. Now recall, electrons have a negative charge. Electrons have a negative charge. So if hydrogen kind of lets its negative charge leave, it has minused its minus. And that gives it kind of a little plus. And this hydrogen allows its electron to drift towards the oxygen, and it's minus, so it's a little plus. And of course now oxygen, which has gained those 2 electrons, has become a little minus. So I'm going to draw this once more for you, a little bit less messy, and I'll do it in a couple ways. So I'm going to draw water a few times. So here's our formula. Water, H2O. Sometimes we will call it HOH because of its chemical properties. We'll talk about that when we learn about acids and bases. If we were to draw it just illustrating its covalent bond structure, we draw it like this. And if you want to look at how it looks in terms of its electrons, we would draw our oxygen here, and we would put its 6 valence electrons there. And I'm going to put my hydrogen here. And I'm now going to use blue ink to represent hydrogen's electrons so that you can see it. And those electrons are going to crowd the oxygen side and kind of leave the hydrogens. The end result is that the hydrogen side is a little bit positive. The oxygen side is a little bit negative. Because we can look at water like this, if we were to think about it like a bar magnet. We sometimes talk about magnets having a north side and a south side. And really what we're saying is that one side is negative and the other side is positive. And we refer to these as the poles of the magnet. And we can look at water and say that water has poles. It has a negative pole and a positive pole. And we use a word to describe that. We say that water is polar. And to be polar means to have an uneven distribution of charge. Well, this uneven distribution of charge gives water all sorts of interesting properties that we will investigate in lab, in class. But we can list some of those properties out. They exhibit something called surface tension. So water has water exhibits something called cohesion. Adhesion. Water exhibits something called capillary action. And water has a high heat capacity. I'm going to encourage you to look these up in your text. And they'll also be a part of lab. But the reason why these things exist, surface tension, cohesion, adhesion, capillary action, heat capacity, they exist because water is polar. That's a P. So I'm going to leave you with one last thought about water. I want to show you how more than one water molecule will interact with another water molecule. And then we'll investigate water a little bit more in class. So here's a water molecule, and I've got the plus charges listed on the hydrogen and the minus charges listed on the oxygen. And if I were to have another water molecule and it were going to begin to interact, it might do something like this. And another water molecule might come in and it might do something like this. And one over here might do something like this. And I'm just going to kind of spin them and line things up. Hopefully it will allow me to do that. There we go. I'm going to line things up a little bit, make it look a little pretty. I'll do one more. So notice that they get spaced out, but how they're lined up. That the positive and negative sides are lining up with each other, but the same charge sides are being repelled. So I'm going to use the yellow ink, which is a little bit harder to see, but I'm going to put some dashed lines here. Oh, let's try again, sorry. Yellow ink, dashed lines, boom, 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 boom. Trying to connect the positives with the negatives. Boom, boom. Notice they're not solid lines like our covalent bonds. Well, those little yellow dots, those are our hydrogen bonds. And they create the weak attraction. These bonds constantly form and break and form again. And it is what makes water bead. It's what makes water attracted to itself, and it's what makes water so good at dissolving. So in this discussion today, we were looking at the difference between covalent bonds and hydrogen bonds and what's causing the formation of those hydrogen bonds. And with that, I'll see you next time. This is Mr. Leventhal. Go take a bath and enjoy that water.